Something astonishing has unfolded as 3 Atlas hugged the Sun's influence in a way that seemed at first glance impossible. That interstellar wanderer sliding into our solar system on a hyperbolic trajectory has just executed a cosmic act that challenges expectations about comets, interstellar bodies, and how they respond to solar heating. 3 Atlas, the third confirmed interstellar object ever observed, has all kinds of surprises. We have only seen a handful of blurry shots, but there are unusual chemical signatures. It is producing way more nickel than iron, and scientists do not really know why. It carries a name that signals both discovery and mystery. It was detected by the Atlas survey system, and the 3 marks it as the third known visitor from beyond our solar domain. 3 Atlas was discovered on July 1st by the NASA-funded Atlas survey. Its path is not a gentle ellipse but a hyperbola. This is not a body captured into orbit, but one that flings itself through, never to return. As it approaches perihelion, it draws ever closer to the Sun, and that moment of closest approach promises to be the stage for something extraordinary. What makes the recent behavior of 3I Atlas so extraordinary is that it appears to have activated in a way no other comet has quite before. As solar radiation intensifies, comets typically begin to sublimate. Ices transform directly into gas, carrying dust and volatiles away to form a fuzzy coma and eventually a tail. But 3I Atlas has revealed a coma overwhelmingly dominated by carbon dioxide, with water vapor, carbon monoxide, and other volatiles playing secondary roles. Infrared spectroscopy from the James Webb Space Telescope captured this dramatic dominance. The mixing ratio of CO2 to H2O in the coma is an outlier, far greater than what typical solar system comets display, suggesting that 3I Atlas's nucleus is intrinsically rich in CO2 or has structural features that suppress water emission relative to CO2 sublimation. As it draws nearer to the Sun, the comet does not simply emit in a symmetric halo. There is evidence of enhanced outgassing in the sunward direction, a plume of dust and gas preferentially pushed toward the sunlight side. That is surprising because normally, the pressure of sunlight pushes material away from the Sun, forming a tail in the anti-solar direction. Here what is being seen is an anisotropic sublimation front, an asymmetric release of material stronger in the sunlit hemisphere. This manifests as a sun-facing feature, a plume rather than a typical tail, and betrays unique thermophysical properties of the nucleus, perhaps rooted in composition, surface layering, or insulating materials. Even more confounding is a phenomenon called an anti-tail, an apparent tail that seems to stretch toward the Sun. But this is not merely deceptive geometry. In the case of 3I Atlas, the anti-tail may stem from the asymmetric sublimation and survival of ice grains oriented in the direction of the Sun. Because in the sunward direction, the sublimation mass flux is stronger, grains ejected toward the Sun may survive longer, form extended structures, and thus create the visual effect of a tail pointing inward. The physics of sublimation, anisotropy, and grain survival can produce such anti-tails not as illusions but as real, structural features in the coma environment. Perhaps most dramatic was the signal that 3I Atlas switched on suddenly during its approach. Some of its volatile releases are rising in a superlinear fashion, not in a smooth, gradual heating curve, but in a threshold-driven burst as certain temperature thresholds are crossed. Observers noted that as the comet warms, emissions of cyanide, CN, and atomic nickel vapor surge in a manner not simply tied to solar flux. The appearance of these species and their dramatic increase at specific heliocentric distances suggest that some process was latent until a critical heating point at which dramatic outgassing erupted. That behavior, basically turning on more violently than classical comets, is what gives the impression that 3I Atlas has done something impossible. As it approaches perihelion, 3I Atlas will reach its closest distance to the Sun around October 29, 2025, at about 1.36 astronomical units, positioned between Earth's orbit and that of Mars. At that point, its velocity relative to the Sun will be maximal. That is the moment when the Sun's heat and radiation pressure act most strongly, and when the comet's internal dynamics face the greatest stress. This event, 3I Atlas doing the impossible, is not only about extraordinary emissions, but about how an interstellar nucleus reacts under solar forcing in real time. For comets formed within the solar system, models of layering, volatile stratification, and erosion dynamics are grounded by decades of observation. But 3I Atlas is not bound by those histories. It carries the memory of a different birthplace, possibly irradiated or altered in unique environments. Its behavior could be dictated by exotic ice mixtures, unusual porosity, internal layering of unexpected chemicals, or structural brittleness under thermal stress. The fact that CO2 dominates and water is suppressed relative to expectations suggests that the nucleus's thermal conductivity, porosity, or insulative layering may be extreme. It means heat may be channeled in ways that trigger steep gradients, causing sudden outbursts when thresholds are crossed, rather than smooth transitions. The result is the triggering of switch-like behavior and volatile release that classical comet models do not normally predict. Polarimetric observations add another layer of mystery. 3I Atlas exhibits an extremely deep negative polarization at small phase angles, values and behavior not matched in typical comets or asteroids. That degree of negative polarization at low phase angles suggests that the scattering and reflective behavior of dust and ice grains in its coma are unusual. The light may be strongly oriented in the Sun-Comet observer plane under specific geometries, indicating unique combinations of grain size distribution, composition, porosity, and internal structure. In other words, not only is the gas release unusual, but the microscopic behavior of dust and ice grains is exotic compared to known comets. In tandem, photometry and careful brightness monitoring show that throughout its inbound route, Atlas has brightened substantially, not in a gentle linear way, but in fits and surges that correlate with heating thresholds. That suggests that internal stresses, pressure buildup, and crack propagation may be occurring, fracturing icy layers or opening vents in ways not seen in ordinary comets, perhaps because of unknown internal layering or high levels of volatile pressure. As it approaches perihelion, such behavior could intensify, especially as thermal gradients steepen and the Sun's influence overwhelms internal cohesion. Another astonishing wrinkle is that this comet began releasing water vapor and showing signs of activity when it was still far from the Sun, at distances too cold for classical water ice sublimation under normal expectations. That early leakage implies that volatile ices of species more volatile than water, like CO2 or CO, or other exotic species, are present closer to the surface, and perhaps overlying materials limit thermal conduction. So even moderate solar heating triggers unexpected early outgassing. In effect, its preparation behavior is inconsistent with simple comet models calibrated on solar system comets. This is the cosmic drama, an interstellar body behaving more wildly, more unpredictably, and more threshold-driven than anything seen before. As it nears the Sun, 3I Atlas is not simply glowing and sprouting a tail. It is transforming, breathing, reacting to a heating environment in real time, revealing internal secrets. The impossible here is that it is crossing boundaries between comet behavior categories, surpassing expectations from solar system analogues. Because it is interstellar, the stakes are higher. If this behavior reflects materials, structures, or processes alien to our familiar comets, it hints at how bodies in other stellar systems evolve. The richness of CO2, the suppressed water, the intense threshold emissions, the asymmetric plume, the sunward features and anti-tail, and the exotic polarization all converge into a signature unlike anything catalogued.